All right, this morning our focus is on water and why water is so cool. No pun intended. Um, the reason why we care about water is simply because biology happens in water. Our bodies are composed of 60% water, and everything that's going on inside has to deal with water and whether something is soluble in water or something is insoluble in water. And so, water and understanding the properties of water becomes very important in understanding how the body works. We can break down some of the key properties of water into four principal topics: cohesion, adhesion, surface tension, and lastly, heat capacity. And the thing that we want to recognize and understand is all of these attributes are given to water because of one thing, and that is hydrogen bonding. Now, let's remind ourselves what hydrogen bonding is and why it's so important. If we think about what a water molecule looks like: oxygen, hydrogen, hydrogen. There's H2O. Examining these bonds from recent lectures, we should be able to see that because of our rule for electronegativity, remember that rule is oxygen is greater than nitrogen, which is greater than carbon, which is about the same as hydrogen. This is electronegativity. We see that oxygen and hydrogen have very different electronegativities. In fact, oxygen is way more electronegative than hydrogen. As such, this establishes a polar covalent bond. It establishes a dipole in which the electrons tend to hang around more oxygen than they do around hydrogen. And what that does, because electrons are negatively charged, that creates a partial negative on the oxygen side of that dipole and a partial positive on the hydrogen side of that dipole. Of course, the same thing is happening through this axis here. So we have partial positive, partial negative. Now the hydrogen bond happens not to create oxygen. Oxygen is held together by those polar covalent bonds, but rather to hold water to itself or to other things. Let's put another water molecule. We have that same scenario through that axis. We have here a partial negative charge on the oxygen and partial positive charges on the hydrogen. This is important because now we can clearly identify the hydrogen bond. The hydrogen bond is an intermolecular force. I made a video about this. You can go back and look at it. It's an intermolecular force that holds these two water molecules together. And by looking at water, you can see that it has the capacity, one water molecule has the capacity to make four different hydrogen bonds, one for each partial charge. So we've already seen this one, but we also have this one, and this one. Now, in liquid water, the reason that liquid water is runny is because water is holding itself to other water molecules, but these hydrogen bonds are weak and they break very easily. I think the average bond length in terms of time before it breaks is in the femtoseconds. So they break, they reform, they break, they reform, they break, they reform. That's what gives water its liquid properties. However, when it becomes solid, all of these hydrogen bonds are locked into place. And so in a water crystal, all four hydrogen bonds are being made. In liquid water, the average for any time, because they're breaking and reforming all the time, is like 3.2 hydrogen bonds per water molecule. Transitioning into steam, that's all we're doing. We're providing energy to break these bonds and liberating individual water molecules from the surrounding other water. And as they break off, they rise as steam. So that's the idea behind hydrogen bonding. And we see now, when we go back to this list of water properties, cohesion. This is water sticking to itself. We just showed that that happens through hydrogen bonding. Adhesion. This is water sticking to other things. Again, hydrogen bonding. Now, water's not going to stick to everything. It sticks to some things very well. It sticks to other things not so well. But understanding hydrogen bonding allows us to predict what it would stick to well. Water likes polar charged things. Surface tension is a little bit different. To understand surface tension, let's consider here, maybe there's a lake, and we have on top of this, you have a little water skeeter, and he's just chilling out, and he's walking on water because for some reason water is really, really tight right there at the surface. Of course, underneath we have all of these water molecules, and they're all holding on to each other, right, through hydrogen bonding, just like we discussed. There's a hydrogen bond here. We don't want to draw it like that. I'm going to draw it with 3 little dots. There would be, hydrogen bond here, another water molecule up here. Anyway, all of this is happening, but these bonds are actually tighter on the surface. Why is that? What's the difference between cohesion and surface tension? Well, we have to think about what's on the other side. So if we explore what air is composed of 79% nitrogen. And what does nitrogen look like? Triple bond, nitrogen. 21% oxygen. And what does oxygen look like? O2. Oxygen, double bonded oxygen. As we look at those two molecules, what can we see? What kind of bond is that? Of course, we can identify that as a non-polar covalent bond. We know it's nonpolar because there is no difference in electronegativity between those nitrogens. They have the same electronegativities, or the oxygens, the same electronegativities. Therefore, they share those electrons equally, and it's a nonpolar bond. Well, water doesn't like nonpolar things. In fact, water hates nonpolar things. Oxygen, nitrogen, these things don't play very well in water. And as such, they resist each other. Okay? These things, water and these gases, they don't like each other. And what that does is when water is forced right here at this interface, right? We've got some oxygen gas, we've got some nitrogen, got some more oxygen over here. At the surface, where these two things are forced to play together and they don't like it, they become introverted and they start to really pull in tightly. And that's why right there at the surface, the water tension is so high, allowing for things like water skeeters to actually walk on water. Now, the last thing we want to talk about with water is heat capacity. Heat capacity is simply defined as the amount of energy required to increase the overall heat of a substance. That's what heat capacity is. Water, because it's so special and because it's so important, it actually has its own unit, and that is a calorie. Small c calorie. This equals the amount of energy required to raise 1 gram of water by 1 degree Celsius. Now, a couple of things just to illustrate that point. What if I had, for example, 10 calories worth of energy? What could I do to 1 gram of water? If I put that into 1 gram of water, this would lead to an increase of that gram of water by 10 degrees Celsius. What if I took that 10 calories of water and I applied it to 10 calories of energy and I applied it to 10 grams of water? Well, that 10 grams would go up in temperature by 1 degree. And so you can begin to see the relationship. What if it was something right in the middle? What if I applied it, for example, to 5 grams of water? Well, that 5 grams of water would take that 10 calories of energy, and you would see an increase in temperature by 2 degrees. There's a couple of things that we need to point out with this. Number one, this is actually very high. In other words, water has a high heat capacity. Water has a high heat capacity. What this means is that water can absorb a lot of energy without changing temperature very much. We see this a lot, especially if you live near the coast or even near the Great Lakes. I saw this in Chicago. It was always 10 degrees cooler downtown during the summer, but 10 degrees hotter downtown during the winter compared to the suburbs, right? We're just separated by a few miles. And this was because Lake Michigan had the ability to absorb energy. During the winter, it would absorb sunlight and radiate that heat slowly to keep the downtown warmer. And then during the summer times, again, it would absorb all that energy so that the energy wouldn't be transferred into the city and maintain slightly cooler temperatures. So water has a really, really unique capacity to absorb a lot of heat. Now, we talked a little bit about what it takes to boil water, right? Where does that heat go? That heat goes into these hydrogen bonds, and it takes quite a bit of energy to break all of these hydrogen bonds and get them finally wiggling fast enough to where they can't hold hands anymore. To make a comparison, let's consider boiling water in a cast iron pot. Metal has a low heat capacity. In other words, you apply a little bit of heat to it and the temperature changes quickly. And so consider making your favorite ramen noodles or maybe a package of Jello. You're boiling water and you get to see where the water's maybe just starting to have a few little bubbles in it. If you put your finger in the water, you could hold that finger in there for maybe 10, 15 seconds before it became uncomfortable and you had to pull it out. At the same time, what if you grabbed onto the pot? The pot would scald you, it would burn you immediately. Why? Because the pot has a lower heat capacity. The same amount of energy is going into the pot as into the water, but the pot heats up faster. In fact, that's what we look for in good quality pots. They heat up really fast so that they can start to transfer that energy to water, which takes a lot longer to heat up. Again, the key point is all of these attributes of water, cohesion, adhesion, surface tension, heat capacity, they all come from hydrogen bonding.